Hello, hello, everyone. Oh, I thought I thought I wouldn't have anyone today. Right. Too close to Christmas, but okay, here you are. Right, so let's get to it. I might do a slightly shorter session today. There's one addition to the assignment, and this is Fresnel's law. And I'm going to share my screen. And okay, please let me know if you can. Do you see my screen? Perfect. Okay, so polarized light. So who has done the topic of polarization of light in school? Yes or no, please. Polarized light. Okay, so you've all done. So you all understand the basics. So light is a wave which contains the oscillating electric field and a magnetic field. So that's electric field. And it's changing in space and time. And this is the magnetic field. And conventionally, we say that the direction of the electric field is the direction of polarization. So in this case, this wave is vertically polarized because the electric field is oscillating up and down. So vertically polarized wave, light, to be more specific, vertically polarized light. You probably also know that only transverse waves can be polarized. And has anyone studied Malus's law in school? Malus's law, let me know, please. This one. No. Okay. So I'm guessing you're doing A levels, because if you were doing pre-U, for example, you would study Malus's law. So it's spelled Malus law or Malus's law. It's different spellings are possible. Right. Basically, let's look at a simple example. We have light polarized at an angle, falls onto a polarizer. So that means polarizing vertically. And coming out is the light which is vertically polarized. Okay, because the polarizer only allows vertically polarized light through. So basically what happens is the electric field is split into components. And you can see that if this angle is theta, this is E cos theta, and this is E sine theta. So E sine theta cancels out, and you are left with E0 cos theta. Well, E0 cos theta, E0. So E is the electric field. The component of the electric field perpendicular to the polarizer is cut off. Therefore, you're only left with the vertical component, which is E0 cos theta. E0 is the amplitude of the wave. For example, the wave can be E equals E0 cos omega t. This is the wave. This is the or omega t plus kx, for example. Yeah, so the wave equation. And of course, when it comes out, it's multiplied by cos theta. So nothing to do with this cos, because this is just the oscillation of the field. So Jasmine, unfortunately, no. We're having some of us, so there's a multi-stage process, and some of us are quite busy, and unfortunately, it's stuck in the last proofreadings. We're finalizing it, but you can already do the problems. You can already do the problems. Yeah, very sorry that it still hasn't come out, but yes, we'll let you know. But the problems are there, so go ahead and do them. And the numbers could change. Right, but this is the amplitude of light. So if the light of amplitude E0 falls onto a polarizer, the amplitude of the outgoing wave is going to be E0 cos theta. Now, you need to know one fundamental fact, is that the intensity is the energy, well, it's the power per area. Intensity of a wave, so that's the energy of the wave. Intensity of the wave is proportional to the amplitude squared. And this is true for all waves. Intensity of a wave. Jasmine, are you asking about where the problems are? The problems are here on the board, so you can access the problems. Some of them are here, and the remainder are here. So you can study the problems and have a go at them. Okay, I won't be changing the problems much. Maybe just one or two problems will change. Okay. The light coming out, and this is an interesting thing. Well, obviously, if you take a polarizer, polarizing vertically, well, that's the three polarized paradox. So I think I've done the explanation of Malus's law. Sorry, no, I haven't finished. Jumping from place to place. Right, the amplitude is E0 cos theta, and the intensity is proportional to amplitude squared. This is a fundamental fact. I won't go into details of why it is so, but it is true for any waves. The intensity of a wave, intensity in this case, is, well, it's proportional to the amplitude squared, which is E0 squared cos squared theta. So basically, intensity is the initial intensity times cos squared theta. So this is the intensity of light that passes through a polarizer. So quite a simple formula. Why is intensity proportional to a squared? Well, if you take the energy of a water wave, you will see that it is proportional to the energy of a wave is proportional to the amplitude squared. And even energy. If you remember the energy in simple harmonic motion, energy of simple harmonic motion is equal to, well, the kinetic energy plus the potential energy. So kinetic energy plus potential energy, and the potential energy was, so the kinetic energy was 1/2 mv squared, and the potential energy was 1/2 m omega squared x squared. So potential energy max maximum potential energy, was the energy of SHM was equal to 1/2 m omega squared a squared. So, and if the energy of simple harmonic motion is proportional to a squared, yeah, it shouldn't be surprising that the intensity of a wave, which intensity is the energy, technically intensity is the energy per time per area, is also proportional to amplitude squared. Does that explain? Does that make more sense, Edward? Okay. And okay, I'll keep that. And because of that, the intensity of light coming in and the intensity of light coming out is I0 cos squared theta. Now, if you have a bunch of light, so this is the 3 polarizer paradox. If you have a polarizer polarizing vertically, it's sometimes drawn as a vertical bars, which is kind of correct because it consists of molecules, of prolonged molecules, which basically make this sort of shape. And if you have light coming in, which is unpolarized light, unpolarized light, which oscillates in all directions. Coming out would be light vertically polarized. So you begin with unpolarized light like this, and it comes out vertically polarized. So this is vertically polarized light. And let's calculate the intensity. Well, here we can't really use Malus's law because this is unpolarized light. So here we use the idea that, well, if you have I0, this is I0, how much of it comes out? Well, if it's unpolarized, that means half of the light is vertically polarized and half of the light is horizontally polarized. So coming out would be I0 over 2. Okay. So the light incident on this is I0, the intensity, and coming out is I0 over 2. Does that make sense? Please tell me. Because half of the light is vertically polarized, half of the light is horizontally polarized. You only allow vertically polarized light, so it's I0 over 2. Now you have vertically polarized light, I0 over 2, falling onto a horizontal polarizer. And now we can use Malus's law to find how much light comes out. And it would be I0 over 2, that's the initial intensity, multiplied by cos squared, and the angle is pi over 2. It's 90 degrees. So that's going to be 0. So you're left with 0 intensity. 0. And that makes sense. And that's what you experience. If you have 2 polarizers, one polarizing vertically, one polarizing horizontally, and you cross them, you have 0 transmission. And let's have a look. So a polarizer number 1, I believe this is a horizontal polarizer. This is a horizontal polarizer. Now we take another horizontal polarizer, and the light comes through. Now, if you turn the second polarized by 90 degrees, you have 0 transmission. Have you seen this before? Have you seen this this experiment before? Yes, yes. Okay, good. But now you have zero transmission because one is polarizing vertically, one is polarizing horizontally. Now, if you take a third polarizer and place it in front, nothing happens. You still can't, no light passes through. If you place it behind the second polarizer, you still have nothing. But watch what happens when you put it in between. When you place a third polarizer at 45 degrees, you see light passing through it. Have you seen this experiment? Oh, okay, you did. In school or in with your tutor in COMPOS? Okay. All right. With tutor. Okay, perfect. Now, and that's quite an interesting thing because so what's going on? Well, we have three polarizers. You have a polarizer like this, you have a polarizer like this, and a polarizer like this. So 45 degrees, 90 degrees. So light coming in is I0. Light coming in, it's unpolarized. So coming out is I0 over 2. And it's vertically polarized. Vertically polarized. Now, when it goes through this, now this, well, let's say this is vertical polarizer. This is at an angle, and this is a horizontal polarizer. So the angle is 45. So the angle is 45 degrees. So coming out is I0 over 2 multiplied by cos squared 45 degrees, which is I0 over 2 multiplied by square root of 2 over 2 squared, which is I0 over 4. So this is I0 over 4. So the polarizer kind of splits this into a vertical and, well, it cuts off the, well, not exactly, it doesn't cut off the, basically the vertical light can be now split into components in this direction and in this direction. So it cuts off this direction and it allows this direction. So the light coming out, bottom line is the light coming out of this polarizer is now polarized at 45 degrees. So it's no longer vertically polarized light. It's light polarized at 45 degrees. And now light of polarized at 45 degrees falls onto a 90-degree polarizer. Sorry. So the angle between the polarization of light and the polarizer is once again 45 degrees. So the light coming out is I0 over 4 multiplied by cos squared 45 degrees once again. So it's going to be I0 over 8. So an eighth of the initial energy passes through three polarizers if they're placed at 45 degrees. Three consecutive polarizers, 0, 45, 90. Yeah, 0, 45, 90. And you can have even more light passing through if you have more than three polarizers. So let's say you have a polarizer at 0 degrees, then you have a polarizer at 10 degrees, then you have a polarizer at 20 degrees, 20 degrees, 30 degrees, and then all the way up to 90 degrees, 90 degrees. And you will have more light. You'll have more light than I0 over 8. which is crazy. I mean, how come you have because a polarizer is a filter. It filters out. It doesn't add anything. Yeah, a filter cannot add anything. And yet, when you have three consecutive filters, you have less light coming through than when you have 10 filters. And even if you do 90 consecutive filters, you have even more light coming through, which is absolutely crazy. Because how come you can have 90 consecutive filters and have more light coming through than when you have just 3? Now, there is a catch, because the filters have to be perfect, and no filter is perfect. And if a filter is not perfect, some of the light is reflected, which is annoying, and you will have well, you probably end up with less light if you go over a reasonable number of filters, you'll have less light coming through. Okay, because there is, even with very, very good filters, there is always some energy lost as you go through the filter. Anyways, does this explanation make sense on a scale of 0 to 10, please? Like this bit, the I0 over 8. Okay, very good. Now we continue discussing the behavior of light at boundaries. And Fresnel, he's like one of the founding fathers of wave optics. Yeah, so there are a lot of things named after Fresnel. His Fresnel rings, Fresnel bands, Fresnel law, of course, Fresnel equations. And okay, so what he's talking about. Basically, if you open a book on GCSE physics, it will say light at a boundary can be reflected, transmitted, or absorbed. Okay? Light at a boundary can be transmitted, reflected, or absorbed. Now, Fresnel equations basically tell you how much of the light is reflected and how much of it is transmitted. Not touching of how much of it is absorbed. Yeah, so we assume there's no absorption. So ideal scenario, which works well in a lot of cases, in most cases. It's especially good at predicting reflections from non-transparent objects. And most interestingly, it allows you to find the index of refraction of a non-transparent object, which sounds spooky. Like, how can you have if you're not transparent, how can you have a index of refraction? Anyways, when light comes in, we basically split the light into two components. So a light incident at a surface. Incident at a surface. We say it has two components. The component parallel, that's the parallel component. Parallel to what? It's parallel to the plane of incidence. So this is the normal. The plane of incidence. So let me write that down. Component of electric field parallel to the plane of incidence. Now, do you understand what I mean by plane of incidence? Please, yes or no? Good. The plane of incidence is the plane containing the incident ray and the normal. So this plane. So in 3D, you try to draw this in 3D. This is the incident ray, this is the normal, and this is the surface. So it's this plane. Does that make sense, Edward? Okay. And some of the light is reflected, and some of the light is transmitted. Okay. And the light that is perpendicular, well, we can draw it like a dot. Yeah, it's towards us. That's E perpendicular. E perpendicular component of the electric field, perpendicular to the plane of incidence. So it's perpendicular. So it's going in and out of the paper, in and out of the paper. Yeah, the electric field going in and out. Good. And so this light, this wave comes in like this, and the two components behave quite differently at the boundary. So as a matter of fact, the Fresnel equations tell you how much of it is reflected and transmitted. So the fraction of transmitted, of refracted and transmitted. And there's a formula for the perpendicular component. So the perpendicular component behaves like this. So R is the coefficient of basically it's a proportion of light reflected, and T is the proportion of light transmitted. So proportion of light transmitted. Now it's important to understand it's a proportion of the amplitude transmitted. Proportion of light transmitted, reflected, and this is proportion of the light transmitted. So, and you can see it depends on the angle of incidence, of course. It depends on the refractive index of the two media. And of course, we have a similar equation, a similar set of equations for the parallel component. Now, I won't be going through this. So there is a derivation of this formula. You can't access the video, but you will. You will be able to once it's published. Well, you can search Jordan Edmonds' video, Fresnel Law. All right. And if light is not falling at an angle, you have a reasonably simple formula here. So this is for normal incidence. Okay, this is the normal incidence when light falls normally. So let's use these formulae to solve question 1a. 1a. Well, 1-1, technically 1-1. So what are we dealing with? Light falls perpendicularly onto water. What fraction of the light is reflected and what fraction passes through? So we have water, light falls, and some of it passes through and some of it is reflected. We want to know what percentage of light passes through and what percentage is reflected. Now, what we're dealing with, N1 is going to be 1 because that's air, and N2 is 1.33, that's water. So very, very simply, so the Rn is equal to N1 minus N2 divided by N1 plus N2. Interesting. It's a negative value. 1 minus, oh, it's minus 0.33 divided by 2.33. I'm assuming I just take the modulus. Yeah, because interesting. Yeah, because you can have it both ways. You can have denser to less dense, and you still have a reflection. And yeah, okay. And when you have the transmitted, so that's going to be 0.33 divided by 2.33. That's 14% is reflected. So 0.14 is reflected. And Tn is 2 multiplied by N1. Just a second. Yeah, it shouldn't be a problem. So 2 times 1 divided by 1 plus 1.33. So 2 divided by 2.33. that 0.86 transmitted. And it makes perfect sense. Let's see if if this actually holds. So FET bending light. So we are going from air to water. The intensity of the light that passes through, 97.7. And this is 2.03. Well, one thing we didn't. Adam, I'll answer your question in a bit. 0. So yes, this is the amplitude that is transmitted and the amplitude that is reflected, and you have if you're talking about the energy that is reflected, the intensity reflected is I'll keep that out. Intensity reflected is the intensity is the 0.14 squared. So 0.14 squared multiplied by I, which is approximately 0.02 of the initial intensity. Okay, and here you can see it here, 2.03%. This is the reflected. Yeah, so if you take this, you move it to 90 degrees, it's about 2.03 reflected, and the rest is coming through. And you can take just minus that, so 98%. Now, why this does not work with the transmitted light? Because the I transmitted is 0.86. Okay, according to this formula. But this squared somehow does not give, well, this square is not 98%, of course. So I don't have an answer for you right now. I think I've confused myself somewhere along the way. But anyways, you can find the reflected bit. The reflected bit works. You find the coefficient of the reflected light, and you have the coefficient, then you take it squared, then that's the energy or the intensity of the reflected wave. Now, Adam, well, what do you think if this formula is like this? Do you think that all wavelengths get reflected by the same amount? Or maybe someone can help? Feel free to shout out. Yes, the refractive indices are different for different wavelengths, of course. So you have different values here. Okay. Now, before we try to answer the next question, the Brewster angle for water, we look at these two. So when light is reflected from a surface, from a non-conducting surface, and that's important, reflected from non-conducting surface, the light can be polarized. Okay. And it will be polarized horizontally when light is reflected from a non-conductor, it is partly polarized. And it's partly polarized horizontally. So what does that mean? Horizontally, that some of the vertical component is reduced at a certain angle. At a certain angle, it is fully polarized, fully horizontally polarized. Am I using? No, I'm using S in polarized. Polarized is spelled with an S in Britain and with a Z in other parts of the world. At a certain angle, it is fully horizontally polarized. So basically, what does that mean? Well, you have light coming in onto a surface, and it is an unpolarized light, and reflected is polarized. So you have light coming in like this, bam, 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 bam. So polarized in all directions. And reflected is only horizontally polarized light. That means that the index of, the proportion of the reflected light parallel to the plane of incidence is 0. Okay. Do you understand that horizontally polarized light means this? Yes or no? Or maybe on a scale of 1 to 10. Do you understand that this is the same as saying that light is horizontally polarized? Okay. So R parallel is the proportion of light, the amplitude by amplitude, that is polarized parallel to the plane of incidence. That is reflected. So you have light coming in. Some of it is like this, and some of it is vertically polarized. So this is the light that is polarized in the plane of polarization, so vertically polarized. So R parallel is proportion of light that is polarized parallel to the plane of incidence, so vertically polarized. Polarized parallel to the plane of incidence is the same as saying vertically polarized. Polarized. Because the plane of incidence is vertical. Does that make sense now? And the amount of reflected light, basically this is the amount of vertically reflected light is 0. The amount of reflected light that is polarized vertically is 0. Vertically polarized light is not reflected. Reflected. Sorry for my handwriting. Okay, now, and if we substitute that into here, and well, there's an explanation here. You substitute, you make this equal to 0. Make this equal to 0. That leads to this, and then you replace that. Then you use the Snell's law. Snell's law, that n2 over n1 is equal to sine theta I sine theta t, theta refracted, and then you are left with this. Basically, tangent of the angle of Brewster is n2 over n1. So you can study that in a bit more detail. Basically, what happens is that when the angle is Brewster's angle, you have light falling like this, light passing through, and light reflected. And the angle between the reflected light, this is 90 degrees. So this is the incident, and this is the so when this is the Brewster's angle, theta Brewster's angle, this is 90 degrees. Okay. So you know about the critical angle. The critical angle is when there's no light transmitted. Brewster's angle is the reflected light is horizontally polarized. Well, if it's a horizontal surface, of course, is the reflected light is reflected light is polarized parallel to the surface. Okay. And yeah, so the Brewster angle is tangent of the Brewster angle is n2 over n1. n2 N2 over N1. Parallel to the surface, and you're saying parallel to the plane of incidence. So that's different things. Yes, parallel to the surface. Yes, the tangent of the angle of Brewster. And let's have a look. So 2. What is the Brewster angle for water? Would be embarrassing if I the Brewster angle for water. So tangent of theta Brewster is N N2 over N1. So that's 1.33 over 1, which is 1.33. So theta, the angle, the Brewster angle for water, is arctan 1.33, which is tan 1.33, 53 degrees. 53 degrees. I have to double check that. Brewster angle water. 53 degrees. Yes, good. I'm not mistaken. So what happens? So once again, the light, if it's if light comes in at the Brewster angle for water, that's 53 degrees. 53 degrees. This is unpolarized. Polarized. And reflected light will be horizontally polarized. Horizontally polarized. Horizontally polarized. So if light is shining at 53 degrees and you're looking at the surface of the water and you see the sun's reflection, and then you take polarizing sunglasses, which polarize vertically. So if you place vertically polarized sunglasses, you will not see the reflection of the sun in the water. Vertically polarizing sunglasses. And this is especially good for fishermen's. Anyways, people who like to sit on lakes, because if you don't see the reflection of the sun in the lake, you can actually see the fish inside, which is quite nice. If the water is clear, of course. I don't think, don't think I've ever fished and never done fishing in a lake that was so clear that you can actually see through it. But yeah, and you can see polarizing sunglasses, water. So here you are, these polarizing sunglasses. So you can see into the water. Take them away. You see the reflection of the sky. And put the sunglasses on. You can see into the water, which is quite cool. So that's how it is. Now, if it's obviously very rarely light will fall at the Brewster angle. So obviously you will have some reflections, but you will cut off them considerably. Problem 2, light of intensity 800 watts per square meter falls onto ice. So for example, if you go skiing, into the mountains and the snow reflects with an angle of incidence of 60. That's unfortunate because 60 is very close to the Brewster angle. But okay, never mind. Let's why not? Find the intensity of reflected light if the incident light is vertically polarized or horizontally polarized. Yes, this is the only, well, not 53, it's 53 point something. Is arctan of the refractive index. So for diamond, it's going to be a different value. So for example, for diamond, the refractive index is 2.4, so it's going to be different. Partial polarization. All other angles at 53 degrees, full polarization, and not equal to 53 degrees, partial polarization. Well, a partial polarization. So if you have unpolarized light, that means you have equal components vertically and horizontally. This is unpolarized light. So unpolarized. Now, if you take the same thing, and this is partially vertically polarized. Does that make sense? And this would be fully vertically polarized. Fully vertically polarized. Okay. So you have a more pronounced vertical component. That means it's partially polarized. And okay. Find the intensity of reflected light if the incident light is vertically polarized, horizontally polarized. So you have the surface of ice or snow, and light is coming in at 60 degrees. 60 degrees. And you want to know how much of it is reflected. How much of it is reflected. And you have the two formulas for the reflected light. When So which one do we need here? We need this one and this one. Okay, so this is the, well, we will easily see which one is which. You'll see soon. Okay, so this is the component perpendicular to the, so this is the, this is for perpendicular, so that's horizontally polarized light, horizontally polarized, and this is vertically polarized, Okay, horizontally polarized and vertically polarized, because this is parallel to the plane of incidence. Right, so this angle is theta incidence is 60 degrees. And do we need anything else? Oh, oh dear. Assignments. Oh, it's right here. We need to find the we need to find the angle of transmission. Yeah, theta t. And we'll use the Snell's law. Theta t. Theta sine theta I divided by sine theta t is equal to the refractive index, which is 1.31. So theta t is sine 60 divided by 1.31, and arc sine of that is 41 degrees. So theta t is 41.4 degrees. That's the angle of transmission. So the amount of light reflected, which is perpendicular, that's for horizontally polarized light, is N1 cos theta I minus N2 cos theta t divided by N1 cos theta I plus N2 cos theta t. So all you need is just substitute into the equation. So N1 is going to be 1 multiplied by cos 60 minus 1.31 multiplied by cos 41. Let's keep it simple, just 41 for now. So N1, that's 1 multiplied by cos 60 plus 1.31 multiplied by cos 41. And we substitute that in. We get fraction, cos 60 is a half, so 0.5 minus 1.31 times cos 41. Okay, so 0.5 plus 1.31 times cos 41 minus 0.328. So the intensity of reflected light, the intensity of horizontally polarized, is 0.107. So it's approximately 11%, basically 11% of the light is reflected, 11%. So which is 11% of 800 times 800, that's about 86 watts per square meter. 86 watts per square meter, that's the intensity of the reflected light if the light is horizontally polarized. Now, if the reflected light parallel is going to be N1 cos theta t minus N2 cos theta I divided by N1 cos theta t plus N2 cos theta I. So it's just like the Snell's law, just a little bit more complicated. So 1 times cos 41 minus 1.31 times cos 60, 1 times cos 41 plus 1.31 cos 60, and that gives us fraction cos 41 minus 1.31 times 0.5 divided by cos 41 minus 1.31 times 0.5. Oh, plus 0.0707. So the intensity of the vertically polarized light is squared, which is 0.5%, which is approximately 4 watts per meter squared. So you can see a huge difference. If the incident light is horizontally polarized, the intensity of the reflected light would be 0.86 watts per square meter, so which is quite a bright light. And if the reflected light is vertically polarized, a lot of it won't be well, yes. That is why if you have light coming from the surface and you have a vertically polarized filter, so the reflection cuts out the vertical the vertical component, and a vertical filter on your sunglasses will cut the horizontally polarized light. Okay. So right, is that making sense? How much sense is it making, guys? On a scale of 0 to 10, please. How much sense is the whole thing? The whole idea is about using the Fresnel formulas. Okay, let's see if this model gives us the same prediction. So we have light. We'll take 1.33, 1.31, angle of incidence 60. Well, let's first of all measure the angle. It's 41 indeed, so that makes sense. And so it's 100%, 11%. 11% is reflected. So basically this laser must be horizontally polarized, not vertically polarized. 89. Okay. All right. Good. Okay, so we have something. Now, problem 3 Well, problem 3 is completely different. Basically, it says show that this equation satisfies the wave equation as long as omega is v times k. So what's the wave equation? Let's just remind ourselves what the wave equation is. And here it is. And well, why not? Let's do this quickly. Yeah, so you have the wave equation. And you want to know that this function satisfies the wave equation. So let's find df dx first. So this is quite straightforward. This is going to be a, using the chain rule here. So f, I'll just copy this down, a e I omega t minus kx is a complex. This is a complex function, and fx, so a multiplied by I ik minus ik multiplied by e I omega t minus kx. Now the second derivative, using the chain rule again, minus, actually, you know what? No, it's fine. Okay. Differentiate this again, I get minus a, so it's plus a I squared k squared e I omega t minus kx. Okay, and I squared is minus 1, so that's minus a k squared e. Oh no, it doesn't. It has the same differentiation, omega t minus kx. It's one of the beautiful things about complex numbers, complex calculus. Now we do df on dt, which is a very similar thing. So there's no minus, so it's going to be a I omega e I omega t minus kx d squared f dt squared, the second derivative. So it's a I squared omega squared e I omega t minus kx. All right, so, and this I squared is minus 1, so it's minus a omega squared e I omega t minus kx. And just substitute. Okay, let's use a color. So substitute this into here and substitute this into here. Substitute. And what do we have? We have minus a k squared e I omega t minus kx equals 1 over v squared multiplied by minus a omega squared e I omega t minus kx. This cancels. Minus a cancels, and we're left with k squared is equal to omega squared over v squared. So omega is equal to kv, which is true. Well, plus minus technically, but omega can't be negative. So true. So this is a wave equation. And as a matter of fact, if you look at this wave equation closely, you will see something. So let's write this down. F is equal to A E I omega t minus kx. So this is a wave propagating to the right. And if you remember that EI theta can be written as cos theta minus plus I sine theta. So F is equal to A cos omega t minus kx plus I A sine omega t minus kx. And we already know that this is a wave equation and this is a wave equation, and any linear combination of solutions. So if two functions are wave functions, any linear combination. Sorry, if a function is the solution of the wave equation, then any linear combination is also the solution. Okay. So these are two solutions, two different solutions. So this is a linear combination of two solutions. And because it's a linear differential equation, a linear combination of solutions is a solution, which is a beautiful thing. Much deeper than I can go in today, or probably in the COMPOS program, but yes. All right, so I hope you found this useful. Have a lovely holidays, and I'll see you in January. Have lovely holidays. I'll see you in January, and yeah, enjoy. We'll publish. I'm going to publish assignment number 5, hopefully this week, and maybe early next week. So you have some stuff to do over the holiday season. Okay, see you everyone.
You know how you said about light being horizontally or vertically polarized when it gets reflected off water?
Yes.
Why didn't you talk about light being horizontally? Or no, you said it's always horizontally polarized, isn't it, once it's reflected off water? But why? How come you didn't talk about light being always vertically polarized? All of it being vertically polarized. Is that not possible for it to be?
No, it's not possible that a reflection is vertically polarized. Only if it's only vertical. So in order for light to be vertically polarized when it's reflected, you have to have vertically polarized light to begin with.
Isn't that the case? Because when you've got light coming into, say, a lake, it's just not polarized, it's unpolarized. So you've got light oscillating in all directions. So surely why wouldn't it be possible for the reflected light to be vertically?
So it is. I mean, if you have vertically polarized light to start with, it will be vertically polarized. The reflection would also be vertically polarized.
So then how do the people that make sunglasses know which way to put the filters in? How do they know that light will always be horizontally polarized?
Because it will always be horizontally polarized.
Yeah, but why though?
Because well, it's to do with the electrical properties of the surface of the material, the way the electric fields behave inside. You cannot have, so basically because you always have unpolarized light to begin with, because the sunlight is unpolarized, right? And if you look at the reflection of the horizontal component of the horizontal component is going to be n1 cos theta I minus n2 cos theta t. So n1 cos theta I minus n2 cos theta t. This will not this cannot equal to 0. Let's see why. So this is equal to 0. So cos theta I minus n2 over n1 cos theta t is equal to 0. So cos theta I minus n2 over n1. So that's sine theta t sine theta I cos theta t is equal to 0. So you're left with cos theta I equals, well, you're left with cos theta I sine theta I equals sine theta t cos theta t, and you, so that means sine theta I equals sine 2 theta I sine 2 theta t. So either you have theta I equals theta t, which is pointless, or you have 2 theta I equals 2 theta t. Sorry, pi minus 2 theta t. So theta I equals pi over 2 minus theta t. So theta I plus theta t equals pi over 2. Right. Have I made a mistake somewhere? What's theta I? I think I made a mistake here. Cos n2 cos theta t, n2 over n1. Of course, I've made a mistake here. It's theta I over theta t, theta I theta t, and that makes that if you divide, so it's yes. So from here, I mean it's a bit mathsy here. You have cos theta I sine theta t is equal to sine theta I cos theta t. In other words, tan theta t, tan theta I equals tan theta t. So theta I is equal to theta t, which doesn't make any sense, or theta I is equal to theta t plus pi. Yes, and that is not possible. Not possible. You cannot have a situation where tangent theta I equals tangent theta t and the angles are not equal. Does that make sense? You can't have the tangent of the angle of incidence equal to the tangent of the angle of refraction, theta I, theta t. Yeah, okay. Yes, see you, Jasmine. You cannot, do you understand, Edward?
Yeah, I get it. That it doesn't. You're saying that it doesn't make sense to have. Well, you could have theta I because theta t if they're the same
If
material.
they're the same medium, but there will be no reflection if they're the same material.
Oh. Oh yeah.
Yeah, if it's this situation. Like if you have have I switched off my? Yes, I have switched off. Well, anyways, I'll share my screen again.
No, I can see it. Like you shared the whiteboard.
Okay. Yeah, there will be no reflection because it just goes straight through if it's the same. Yes. This makes no sense. Makes no sense. So or no reflection. Reflection in this case. And in this case, it's just not possible. Because you can't have two acute angles and one of them being 180 degrees greater than the other one. Okay.
All right. So in conclusion, I learned from that when light gets reflected off water, it's always horizontally polarized. At least.
Well, the correct way to say it's polarized perpendicular to the plane of incidence. So you can stick to that definition. That's a bit more useful.
Parallel to the plane of incidence.
Perpendicular to the plane of incidence.
Oh, okay.
Okay.
Okay, thank you.
All right. See you. Have a good
Thank you.
Christmas.
Yeah, you too.
See you. Bye.
Bye.